Or do you want to go first, just since I know you had a slide to present, and then we'll switch to Jeffrey?
Sure. Yeah, I'm happy to. Oh, this lighting's rough. All right. Yeah, don't have much to say, just a bit of an introduction into the LISA sources, what challenges we're going to face that probably aren't LISA specific, but are different than the challenges we face with LIGO at least, and what needs those translate to for waveform generation. So LISA expects to see a lot of different sources. Naturally, we have massive black hole binaries, extreme mass ratio in spirals, intermediate mass ratio in spirals, galactic binaries, stellar origin black hole binaries, as well as other transient signals, and hopefully potentially beyond GR sources. You can see on this bottom left plot how some of these different signals lie within the noise curve. And you can see that for some of them, for like the massive black hole binaries, for example, depending on their mass, they can be within the LISA band for hours up to years, potentially, which will come into some of the challenges that we're going to face. So because I do massive black hole binaries, that's going to be primarily what I'm talking about here. But so some of the challenges that we're going to face, because we're going to have signals in there for hours, months, etc., we're going to be having a lot of overlapping signals. And that's going to make it really important that when we are modeling these signals, we have very low errors, because it's possible that when subtracting out a louder signal, you could potentially contaminate other signals below it if you don't have a accurate enough template, which also ties into loud signals. I don't have a plot in here, but we expect LISA to see signals with SNRs in the hundreds up to SNRs of 3,000 potentially. And while that's great for actually being able to measure the parameters of the system, it also poses challenges, because any mismatch that you have between your model and your template and your signal, any residuals that might remain can be significant in terms of SNR, and again, either skew things like tests of GR or potentially contaminate other signals. We're also going to have very long signals, and that poses a challenge, because right now with numerical relativity, we tend to, well, actually, you can kind of see down in this bottom right plot is kind of useful for this. When we talk, we've got orbital frequency on the left, and we've got symmetric mass ratio on the right, on the bottom. And it shows what regions of parameter space different techniques are best suited for. And given that this is the ETK, we're primarily thinking about numerical relativity here. And we tend to only go up to separations no more than the peak here is around 20. And so for signals that are much longer, we're going to need to either figure out how to run longer simulations without accumulating error and hopefully making them more efficient, or figure out the best way to hybridize and what errors might come into play when we hybridize waveforms. We also expect significant eccentricity within the LISA band. We expect some eccentricity potentially even within the LIGO band, but with LISA, we definitely expect to see that. And so that's a whole area of parameter space that we need to address. Similarly, there are recent studies that seem to expect high spins for the binaries that we expect to see within LISA. And so that parameter space also needs more coverage. So I've already addressed some of the needs as I discussed the challenges, but improved waveform accuracy for detection, parameter estimation, and contamination purposes. Longer waveforms, expansion of the parameter space into, and denser catalogs as well, into eccentricity, pushing the mass ratio, because there's that tricky bit of parameter space where self-force simulations aren't, well, actually new developments, they do seem to be able to go to much lower mass ratio, but there's still this gap where we want to make sure that we, beyond mass ratios of, hundreds, but not up to the mass ratios of thousands, that gap where we need to make sure that we are able to produce waveforms, the intermediate mass ratio regime. And for all of these things, we also need more efficient simulations because we need very dense catalogs, and we need to make sure that we're able to actually accomplish those. And then similarly, we need beyond GR catalogs as well as catalogs that address matter effects. Because if we're not even modeling or simulating everything within GR, we can't be confident about anything that or it's harder to be confident about anything that we perceive as a beyond GR effect. And in terms of the impact of some of these accuracy requirements, this plot in the middle shows how if you inject or if you compare a high resolution waveform and a low resolution waveform, here in the black and the blue, you can see the residual here in the shaded blue. And then if you compare that same high resolution template to the same one, but including only the 2-2 mode, so ignoring overtone or ignoring higher modes, you get this red residual. And you can just see that they are of comparable magnitude. And so having low resolution waveforms can be just as significant as ignoring higher order modes. And we know that that's very important. So this is definitely a topic that will need to be addressed to make sure that we're not missing anything or skewing anything. So that's just a brief overview of what I see as the challenges from the LISA perspective. I'm sure other LISA people will have a lot more to contribute to this as well, but that's a bit of a start.
Thanks. I appreciate the summary from the LISA perspective. Are there any questions being generated yet? I don't know if people want to kind of go through a bunch of slides or start asking questions. So I'm going to leave it open for a second and see if anyone has specific questions for Deborah. Sorry, I'm looking at everybody's pictures right now, and I just saw David Nielsen's Zoom image is fantastic. I just have to say, David, that's pretty fabulous. Sorry, as I entertain myself with all your pictures. Now you all have to go look and try to find David Nielsen's. No. As we go through this, like right now, this is a nice summary of sort of things from the LISA perspective. And Deborah, if you want to go ahead and stop sharing, we'll get ready for Jeffrey. I want to remind ourselves, so we don't forget to do this, that we should also talk about format, because of course, as we build, it'd be really nice if we didn't have to have 3 or 4 different numerical relativity formats going at the end of the day when we have all these fabulous gravitational wave detectors going. So let's just note to selves, I'll write it down. Let's remember to chat about that later. Jeffrey, do you want to take over?
Hello, can everyone on Zoom hear me?
Yeah. Hi.
Okay, so I wanted to start out just by showing this this plot from Borean and Sathya. This is with Cosmic Explorer, which I'll say a little more about exactly what it is on the next slide. It has a lot in common with LISA and Einstein telescope in terms of waveform modeling needs. So rather than repeat the points that Deborah just made that we all have in common, I just wanted to throw out some things specifically from the Cosmic Explorer perspective. So this slide is a plot of how many loud in orange or how many really loud signals in green you could expect to get from different detector networks. This comes from a trade study that was done as part of Cosmic Explorer, where they looked at different detector configurations and different sources. And basically, if you had a network of 2 next generation detectors, like Einstein telescope, well, actually just one next generation detector like Einstein telescope or Cosmic Explorer plus today's network, then you would still expect to get something like 10-ish very, very loud waveforms, where that means more than a signal to noise ratio of 1,000 every year. And so one big thing that motivates a lot of the science potential for Cosmic Explorer is these very, very loud signals, because that opens up a potential to look for new physical effects, like effects beyond general relativity, for instance. So what I wanted to show you here, I'll walk you through a few things on the slide. For those of you who might not be familiar with Cosmic Explorer, briefly, the idea is to take the technology that's successful for LIGO and just scale it up. To build, instead of 2 4-kilometer detectors, build a 20-kilometer detector and a 40-kilometer detector. The reasons why it's beneficial to have 2 detectors of different lengths has to do with the noise curves performance at high frequencies versus low frequencies. 20 kilometers is actually better for the higher frequency things, like for post-merger remnant for neutron star things. And so in the bottom, so I'm showing where Cosmic Explorer and Einstein Telescope fit in compared to other things like LIGO A+ and through there in the top right. Oh, people on Zoom can't see me pointing, so I'm pointing here. And then in the bottom right, this is a figure, this is really just a cartoon. It just is simulated noise plus 150914 like binary black hole waveform from the SXS catalog. And the blue curve is what the unfiltered data would look like for LIGO A+. And the same signal in Cosmic Explorer, you can see the difference. You can just see the waveform without doing any filtering at all. This is exactly the same kind of thing as what we just heard you can get from LISA when it observes these massive black hole binaries. The frequency is different, but black hole binaries modeling is independent of the total mass scale. And so you can just, everything that applies to LISA rescaled applies to Cosmic Explorer as well. And the big thing that I would like to kick out there as a question to talk about is, given that we have overlaps in things like waveform accuracy requirements, figuring out what accuracies we need, maybe the answer is different, but the way we figure those answers out is the same. Figuring out how to achieve those accuracies, is current numerical relativity enough? Are we going to need to improve our current codes? Are we going to need new codes? And once we can do it, how do we make waveform evaluation fast enough that it's actually practical, so that we can make sure that we're delivering, that we're not the blocker for the science goals that these next generation missions have. And so the question is, in that context, what is the best way forward for us to collaborate and coordinate? So that's what I wanted to say with my Cosmic Explorer hat on. If I put on my SXS hat, if we talk about file formats, there are some, SXS has opinions about that we can get to later. Everyone has opinions about file formats and metadata. So that's what I wanted to say for now.
Thank you. Very interesting. I don't think anybody from Einstein Telescope particularly told me they wanted to chat, but if anyone out there wants to, I don't care where you're, anyone wants to chat about anything, they can. You don't have to be associated with one of these future missions. So just, if you want to, just let me know so I can add you in. Otherwise, any questions specifically for Jeffrey? It's a quiet group today.
I had a question.
Please.
I guess my question is, as far as the collaboration with the telescope, is it the Einstein Telescope? How does that work for universities to begin collaboration?
The Einstein Telescope is in Europe. And the Cosmic Explorer is the US one. So it looks like, Carol, did you want to address her question? Or you had your own question?
No, since I'm part of Einstein Telescope, I can say a few words precisely about Einstein Telescope. Einstein Telescope just started a collaboration, and either they will have a periodic call, or I think the application is pretty much always open, that one can apply for membership as a research unit. I'm one of the coordinators for the waveform division of the science board of Einstein Telescope, and improved waveforms, both numerical and analytical, as waveform accuracy is definitely on our priority list.
As far as the Cosmic Explorer, I guess the same question.
Jeffrey, you want to take that one?
Sure, yeah, so Cosmic Explorers has something called the Cosmic Explorer Consortium that anyone is welcome to join. There's a separate Cosmic Explorer project that's specifically focused on trying to get funding and get the design and get the done and get the instrument built over the long term. But the broader work of the community towards the science goals is happening in the consortium. If you're interested in joining the consortium, you can sign up on our website at cosmicexplorer.org. If you have questions about the consortium, there's a questions link right on there where you can contact us. If you want to, if you're interested in waveform related things, I'm the person to talk to for Cosmic Explorer, and we're happy to work with anybody who's interested, any institution. It's the same policy as Einstein Telescope from what I heard from Harold.
Thank you.
If anyone wants to join LISA, it's very similar. There's a LISA consortium, and it's pretty easy to join at the associate level. Means you are not promising any real time, and full membership means you're promising some actual time to the consortium. So everything's pretty open right now, and relatively easy to get engaged, I think. Atul, do you want to go next? Sorry if I pronounced your name wrong.
No, that's almost correct. But yeah, my question was maybe a little bit naive, but I wanted to ask if, so for Cosmic Explorer and both Einstein Telescope, there'll be much better sensitivity, amplitude improvement, but I was wondering what would be the timescale improvements? Because, you know, in the post-merger regime, we want to measure things of the scale of maybe 10 milliseconds or even less if possible. So I'm wondering if those would be measurable, or we are still looking at some things in a bigger time scale. So for example, in the waveform plot that Jeffrey, you showed, seemed like the resolution was great, but I'm not sure what resolution to expect.
I guess I'm not used to thinking in terms of seconds, so I'm hesitating for a second. Because, you know, for us, right, the time scales are just going to change compared to the total mass. So for example, you know, if you looked at the frequency range of LISA, yes, it's the nanohertz, but things last, you know, the orbit is at a different time scale. I mean, in the millihertz, but the orbit is a different time scale than if you looked at 10 to 100 solar mass black hole binary. So we typically use a unit that's massless, so we don't have to do this translation. And then the question is how much resolutions are we going to need? It's going to depend on a lot of things, like how many orbits we have. Did anyone want to answer Atul's question directly? Just unmute yourself.
I can give it a try. So at the high frequency regime, I think both Einstein Telescope and Cosmic Explorer are going to go a little bit higher frequency than LIGO, simply because they're so much more sensitive. You have this extra factor of 2 in high frequency, perhaps to 4 kilohertz instead of 2 kilohertz or so. I'm no expert on the experimental side, but I would expect that going this extra factor of 2 in high frequencies, neutron stars, core collapse, supernova, and those types of systems.
Oops.
Okay, yeah. I guess it makes sense. Yeah, so there's an increase in sensitivity in the higher frequency. So essentially the time scales are also much more improved in the observation regime. So yeah, thank you. Yeah.
It would be really exciting for neutron star
And
mergers. Let's hope for that. Yeah,
of
Harold,
course,
go ahead.
yeah. as I said, I'm not an expert, so please don't quote me on any number I just throw out there.
Zach, you've been waiting a bit. You want to go ahead?
Yeah, so this is in regard to Jeffrey's comment that I think we need to be pushing more toward collaborating and collaborative efforts. Basically, given the extreme level of accuracy that we're going to be needing, we're going to be pushing in our current infrastructures kind of to their limits. And as such, I think it is at least, we should at least, let me just put it this way. I think I'll just throw the idea out there that perhaps for every waveform generated by one code, it would be great if another waveform could be generated using a different code for that same physical scenario as a cross-validation between codes that are being pushed to their limits. And I think that'll give us a cleaner understanding perhaps of the errors beyond just self-validation tests.
Yeah, that's a really good point. You know, so sometimes we say, like, we're used to right now, the current generation of codes, the SXX code is the most accurate, right? But we really do need more than one code. It would be silly for all of us to abandon ship and knock on XXX's door and say, hey, we're all going to join and push with this code. We got to have at least 2 codes, and if not more, especially because we're sensitive, maybe we're better at different regimes or what have you. So I'm trying to find right now a table that we're producing of all the codes that are sort of around or being developed. And so everyone here can get a sense for just how active the community is in either, you know, codes that exist now and ones that are coming. So you guys can see that. So let me see, it's almost hard to get all of them listed. So this table lists, what it doesn't do yet is differentiate between the codes that are already production ready or those that are under development. But there's a tremendous number of numerical relativity codes throughout the world, either currently producing a catalog of numerical relativity waveforms, that's this catalog column, that are already available. So you can see that there's a few, I mean, not a ton, that have produced waveforms. So if you see a citation, that's to the catalog itself. So there's ours, and there's several others. Some of them are binary black holes, and some might have some neutron star information in it. And whether they're open source or not. And see all these different formulations is another key thing. I think what Zach says is really important that we do it, especially as we get to more sensitive detections. The fact that a lot of the nuances between the different codes have not been seen or not yet been important as we look at the current generation of gravitational wave detections. That doesn't mean that as we get to these next ones that we aren't going to see that. So there's a lot of interesting things happening where people are trying to be clever, different, you know, pushing in a lot of different ways. So I just wanted to share with you guys this huge list of codes that are out there. And this is taken from a paper we're writing in the LISO waveform working group. Reference 26 is not published yet. This thing that's already on the archive is called the SNOMAS 2020 Cosmic Frontier White Paper, from all these large studies that are happening. This is like the decadal, but for particle physics. So if you wanted to find that yourself, I'll put it on the chat. That'd be better. I'll stick it on the chat. Apologies for not thinking of that right away. All right. Anyone else want to talk about, push something forward? We have several codes represented here in this room, this Zoom room. But maybe everyone's tired. So I'm going to ask a question and see if you guys will be willing to answer it. I'm curious with this, with how we should go, like, all right, so codes are one thing. Let's say we have several codes, which I hope we do. I hope we have all those codes that are listed and they're all fantastic and doing wonderful things. But let's say a bunch of us are generating waveforms. Do we envision a future? Let's say it's 2030. Are all these different observational consortiums getting waveforms from individuals or part of their collaboration, or is there a large public data bank of numerical relativity waveforms coming from the community? So we're already in the, so everyone in these different observatories will be just grabbing that. So do you guys think there's value in having individual catalogs like the way we do right now? LIGO, Virgo has their own numerical relativity catalog. It's actually different than the one that's the public catalogs that are available. You won't find exactly the same waveforms in those. So what do you guys think? Would it be better to have one big public catalog that all the detectors use, or you'd rather be inside these consortiums producing waveforms? Go ahead, Mike.
Thanks. Can you hear me?
Yeah.
Okay. So I think so one of the problems we've run into in sort of trying to unify all these different things. So back in the days of Ninja 2, I was the one tasked with getting everyone's data together. And so I referred to myself as chief cat herder, because so the problem is everyone has, you know, different pieces of metadata lying around. They prefer their different formats, et cetera. So I mean, it'd be great if we could all agree on, you know, one format and just stick to it. But I think another way forward would be a sort of a meta format approach. So this is something we've tried. So we have this, you know, Python package called SXS, very creatively, and there's this function that just says load, and you give it like the name of one of our waveforms, and then you don't need to care about the format or anything like that, and it just gives you an object, you know, a Python object with all the pieces of data with a common interface. So I think that that sort of interface is something maybe we should strive for, rather than necessarily having, you know, everyone in the same catalog, because just logistically, I think that will be a difficult problem. You know, I have strong opinions on the format itself, you know, especially lately. We're actually switching over to a new format very soon. And so to speak to Zach's comment just now, we put our catalog previously on Zenodo, but they, you know, the maintainers spoke to me and said, hey, cut it out, because we just put too much data on there, which was partially my fault, because, you know, we put out multiple copies of things on there. But, you know, we also need a more compact format and that sort of thing. Mm-hmm. So yeah, it's hard to find, you know, a way forward, I think, that will fit everyone without some sort of centralized, you know, funding from Lisa, say, you know, would be required to be able to just logistically hold all these things, I think. So I think we should have more discussions about just an interface. And then if people have different formats, you know, have some piece of code that could read a given format and output to a different format. And I think that problem basically goes away.
Yeah, and I think I completely agree with you. And I think I was too simplistic. I think what I meant, what I was trying to drive at is, I agree with you. Everyone would have their own, and that there would be these, yeah, there'd be these collective infrastructures that would be able to grab different formats. But do we want to, and we don't have to answer this right now, I just want to clarify, do we want to do this as a public entity, or is everyone going to be trying to do this within consortiums? But anyway, so Leo, did you want to?
Yeah, can you hear me? Yeah, so I guess I just wanted to get clarification on your question, because like the simulation data products, like the waveforms themselves, are not necessarily, you know, useful for Einstein telescope to do analyses. It's useful for somebody in between to like build a waveform model, or to, you know, like calibrate their EOB model, or to build a surrogate or whatever. So who is the intended audience for this, you know, catalog that you are asking about?
So I would say modelers are probably the biggest audience. I agree with you. We also do use, not in the routinely, but we do directly
like
use numerical relativity waveforms in LIGO, right? So RIPT can handle that. And so what we often do is, if things are looking funny, right, something isn't quite clear about the signal, that you have a bunch of, we will all go, a bunch of us will go do a target waveform, target generation of numerical relativity, and see, oh, is there some eccentricity in here, and we just don't have a search for it, etc. So I think we should always leave room for direct communication between NR and the detectors, not always through the modelers, I think. And also one of the things that I worry about is that sometimes I look at the modeling situation and they seem to, they have their own errors. And so is there a sense of what are the errors in numerical? You know, like we aren't perfect. So let's make sure that also the different flavors, if you don't want to choose always the same group's waveforms, are we all being careful that we have, you know, we understand the systematics of things that are happening. So that's my only worry, that we don't go too completely through the lens of only models. But it's an excellent question. Who are the unanswered? And so for example, I want to see Lisa do a mock data challenge, and maybe they need to use an NR waveform, or maybe they need to use a more advanced model waveform and not always just do the post-Antonio or whatever they've done for the last few. But that's just my big thing. Deborah?
That does remind me that while we're thinking about this, there is an effort going on in LIGO that I've been slightly paying attention to, but I'm sure other people here have been paying more attention to, in terms of the interface for waveforms, like model waveforms that people are generating. There's been a big rewrite effort. And so that's something that we'll want to pay attention to and think about as well, because we are both because our waveforms are used for model training and stuff, but also because, like you said, it's useful when NR waveforms can be used directly. And so it's just useful for us to pay attention and see how whatever we develop will fit in with what the modelers are creating this interface for.
Is anyone, are there any people representing the model community here? Maybe not, because this is an NR conference, but I would like to see us also have a better, maybe better ties with that community as well. Maybe some people do it, and it's just that I don't, but yeah. There's a lot of interesting discussion happening in the chat. I don't know if anybody wants to summarize it. I think this was based on the question of how that Steve had about the resource requirements for such a catalog or any catalog, because it can be big.
Sorry. Yeah, to just summarize it briefly, we used up 16 terabytes on Zenodo. That's the point at which they said, hey, cut it out. But with our new data format and reducing the number of things that we put on there, so the new format can compress it, just a single waveform, about 4 times better than even like the best HDF5 sort of nicest things you could do. But then we can go further by just getting rid of stuff we didn't actually need, and that reduces it to maybe 500 gigs for our current catalog, which has about 2020 simulations, I think, each of which has, I think on average, 3 resolutions, each of which has about 4 waveforms. And then there are, multiple copies of the waveform because of CUM correction and stuff like that. So I'm not sure how to answer your question, Harold, other than pointing to our paper. So I think that's the summary.
Deirdre, you're muted.
Thanks. You need someone to tell you. Steve just put up in the link a link to what was semi-public storage. If people want to click on that. If people are curious about potential ways we can do storage. So I guess we have several questions. Let's summarize for a second. I think Steve's big meta question is a good one. If we're going to talk about, we should probably think about what type of requirements in terms of terabytes or what have you, we would need for a beautiful place where Lisa, Cosmic Explorer, and Einstein Telescope are all there, and what type of just pure NR do we think we would need to have? That's a good question for us to kind of ponder. And that drives sort of the format question. So one thing is interfacing with models and the detector, but of course you're right. The big question would be how do we have to compress so that we can fit and be viable? And then the questions of we also have some big questions coming from the astrophysics community, which is coverage of parameter space, so I think eccentricity means something different to me than it might mean to an astronomer, because, if we kept our black holes at the same place and up the eccentricity, we're doing head-on collisions at some point, so it's really hard to do very eccentric with the black holes very far apart going through several orbits. And then the other question being accuracy, but that of course is loaded because it depends on what parameters you're studying, how many orbits are there, there's so many things, what SNR is there, so all those things are driving these questions. And as Jeffrey just put in the chat, indeed, you need a couple compression and accuracy, because you don't want to introduce errors from anything, from the compression. If you're doing some other interpolated catalog, you can't be introducing errors from the interpolation that are larger. So probably for NR community, correct me if I'm wrong, everybody, our biggest problem might be we don't know, we don't have a good measure of accuracy that we can use to start answering these questions. We have a hardcore one, but we don't have one that's like based on the detectors. What I mean by that is we could do a measurement of accuracy based on signal to noise ratio and like matched filtering. And, as Deborah showed you, we can compare two waveforms and tell you this was their accuracy based on their truncation error. But we haven't yet said, and this is the way it would impact parameters, or this is the way it would impact if you were doing a global fit in LISA. And actually probably all these detectors will do global fits because we're going to have more than one event in the same time, which is new for us in gravitational wave community. Alessandro, do you want to say something?
Yes, please, because let me say the following. Let me bring here my experience, which is around this. Because typically, when we calibrate or we inform UB model, we use SXS waveform, and we trust SXS waveform as the best waveform that we have available. Is this true? In doing this, we just recently published a paper with Carlos and Jim Healy. When we have exactly the same kind of waveform, the same kind of mass ratio, Q equals 7, non-spinning, and compare it with SXS waveform, and we found a difference that is maybe not relevant for signal to noise ratio, but is relevant for UB calibration, in the sense that if I hadn't the SXS waveform and I trusted the RIT waveform, I would have gotten a different model. So in a sense, the questions that you are asking are already posed, and what do we have to trust? And the errors there are measured in the usual way, like using Richardson extrapolation, so are errors of the order of 0.2 radians that are already big. They are probably irrelevant from the point of view of the mismatch, but they are relevant at the level of UB models and UB modeling. So, the answer to the question seems to me already there. So there are waveforms that where the merge and redown is good, is consistent, and I think that everybody that uses finite differences code more or less agree on 5 or 6 orbits. But then we have more problems on longer orbits, and it's already there. It's not a matter of saying, is this useful for that signal to noise ratio? Or is a matter of saying of understanding what to do with the modeling, because our modeling is dependent on the accuracy of an R simulation. So we trust an R simulations as exact, and we trust SXS simulations as exact. Is this correct? I think this is the question for the NR community.
I don't even think an SXX person would say
No,
it's
they're not
correct,
exact. No, they're not exact.
I know they are not. I know they are not, but we act as if they were, in the sense that, I mean, as being one of big users of the SXS catalog, I have always the problem of understanding what is the uncertainty. So you give two different resolutions, and they say, okay, I have two different resolutions. I have an error around the merger of 0.1, 0.2 radians over, I don't know, 30 orbits. So my calibration of the model is such that I fit within this little window. So in a sense, I trust you, and all my models are tuned to are such that they are okay with the success. But then when I compare with what can consider, I mean, good waveforms, because of this Q equals 7 that Carlos and Jim have simulated, it has I think 0.2 radians over 10 or 12 orbits. I mean, one has to check the paper precisely. So it's an error that is small, but in my UV modeling, I can see this error, and I can change my modeling. So I could be good with a RIT waveform, but then I become bad with a success. So you see what is the problem. So and from our point of view, there is no problem, in the sense that once that you give me a numerical simulations with a very tiny error, with an error, I can adjust or improve my model so to match the waveforms. I mean, there are situations when we can have, I mean, very, very long waveforms, let's say 30 orbits or so. We can have a new BNR agreement, phase agreement at the merger that is below 0.1 radian, which is, from the LVC point of view, from the LIGO point of view, is indistinguishable. At the level of Einstein telescope, this means mismatches of the order of 10 to the minus 3, 10 to the minus 4, which is still not enough. But the problem is before. So you have to agree, in a sense, among yourself, among numerical relativists, to understand what to improve, to understand what is good and what we can trust. Because of, as I said, at the moment, for me, SXS is the best. Am I right? Okay.
I don't know, right? I mean, for a time, I thought that the SXS wasn't quite as clean at doing merger ring down part. I think since then it's improved. So it's also a function of time. I don't know that, you know, so maybe for what you're doing, SX the best, done deal. But of course, there's a lot of errors, right? So they've got exponential convergence, right? We don't, you know, but they have a different formulation, a different gauge condition. So there's a lot of differences between the numerical relativity codes that haven't come down to being a simple error bar for you.
Yeah.
So that would be great. I mean, I don't blame you for trusting the SXX waveforms, but I don't know that you're ever going to be able to. I think you need an error bar, but I don't know, you're never going to be able to treat the waveforms as perfect. No,
but also the error bars, in a sense, on SXS waveforms are a bit, let's say, random. I mean, when there is this catalog, this beautiful thing that we have at hand, but in some situation we have two resolutions that are close, or let's say you find really an error bar that is of the order of 0.05 radians or so, and so you say, okay, I can go there. In other situation, the error bars are not computed, or there is just one resolution, so, and all that. So it's really hard for us. While, okay, you were mentioning the possibility of comparing codes. This is certainly good, but maybe this is an effort that should be coordinated in some way to figure out what we want to understand. Because also, for what concerns, I mean, in fact, we have in mind Einstein telescope, or we have in mind LISA. So what do we really don't know? This is the point. Because if we think about long in spirals, I mean, at the analytical point of view, we can we know what is missing during longing spirals. So it's a matter of figuring out how correctly model the radiation reaction during the longing spirals. The UV is certainly not exact there. There are things that are missing, but not that much. So we need, on the one hand, long waveforms, very accurate for the spirals. So to check that our modelization is good. And then what else is missing? Is the ring down, or do we still need to understand more things during the merger and ring down? This is a question for everybody. Because for the spiral, sure, we are not ready, I think. There are things missing, and they have not been cross-checked accurately.
Harold Pfeiffer suggests we say our names the first time you speak, since there's so many people. It seems like a nice idea, Harold. And there's a lot of hands up, and I don't know who wants to respond to whatever Alessandra's saying.
Please.
So
I shut up at this stage.
no, I think this is exactly what we were missing, because a big driver of this is the models, and so we need to hear from you. So I'm very grateful that you spoke up, Alessandro. I think it was Zach, Leo, Mike. So Zach,
I just had a suggestion that perhaps for one thing, Zoom chats kind of like to disappear at the end of Zoom session. Would it be a good idea for us to have it maybe either? I would prefer something like a Slack channel, because I think there are some community-wide Slack spaces out there, workspaces out there, and maybe we could add a Slack channel and widely advertise it, so that we can continue this discussion, share data, be a little bit more systematic in areas where we need to be. Just wanted to throw that out there.
and I meant to be having a Google Doc this entire time, so that we saved a list. I will at least try to grab this chat and put it in a Google Doc. Yeah, there is an NR community Slack channel. Maybe that would be the easiest to not introduce a second one.
Or at least there's that workspace. There's the general relativity workspace that the NR community call is in. So I think it might make sense to make another channel and leave that one specific to the NR community call, but maybe have a channel in that same workspace. Just a thought.
And it's a Slack workspace.
Yes.
Okay. Let's do that.
Okay, can I
Thanks,
jump
Leo.
in? Yeah, so this is going back to responding to what Alessandro was talking about. So I think the thing that we need to discuss is, quantifying our error budgets, right? This is something that experimentalists are very good at doing. We can see like how much of the noise in the detector is due to radiation pressure or whatever, right? So, we have our own convergence errors. We don't yet have some like very precise way of saying, okay, so codes are converging to something. Maybe there's a subtle bug in the code. It's converging to the solution to some wrong differential equation, whatever. So of course there needs to be cross-validation errors, which is, I think, one of the things that we all want to do. So we need, as Mike suggested, everybody should open pull requests on the SXS package so that everybody's data formats can all be loaded into the same Python module, into the same types of objects. And then we can start to actually quantify things and say, over here in parameter space, everybody is converging to the same thing. So, if you are calibrating your waveform model to something, then you know that the error budget over here in parameter space is going to be no greater than 0.1 radians over however many orbits or whatever it is that we want to quantify. But to do that, of course, there are issues about subtle systematics that haven't yet been addressed in everybody's codes, which is that everybody is, as far as I know, that we like to present our data as spherical, spin-weighted spherical harmonic coefficients, which means that we actually have to know what BMS frame they're in so that we can do cross-validation correctly, or to all transform to some standard frame. So we can do that with SXS data. Well, we can do that with any data that has been, that's used Cauchy characteristic extraction. So we can fake it with extrapolated data, but it's something that we can do. So maybe, once we start trying to do this, we'll actually find out that our errors are, actually our cross-validation errors are above the point of even worrying about getting things into the same BMS frame. So I shouldn't even be talking about that. But I guess we can't say that yet unless we actually have all of the data in the same package, in the same types of objects. So actually, okay, I'll shut up now. I've been rambling too long.
Mike, you want to chime in?
Yeah, so on a related topic, yeah, also speaking to what Alessandro was saying, I think there's a really simple example, even if you're just talking about SXS waveforms, which is all I usually do, and I apologize for that, but just looking at our waveforms, we have these various extrapolation orders, right? And so it's a simple example of how this is a problem, sort of deciding what our error criterion is just looking at those different extrapolation orders. And, if you're looking at early in the in-spiral, you actually want, usually you'll want higher order extrapolations because they do things removing near field effects that are largest in the early in-spiral. But then if you look at the ring down, for example, you basically don't need extrapolation, and putting extrapolation in just sort of adds to the noise, essentially. It magnifies noise. And so you want lower extrapolation order. So the message there is it really depends on exactly what you want. And our grad students are always come in and say, come on, Mike, just tell me which one I should use. And the honest answer is use all of them and see, see what effect it has on your results. Whatever your results are, maybe you're hybridizing, maybe you're comparing to ring down, whatever. You need to incorporate all these different waveforms into your error estimate. And that, I think, that would be a great application of Zach's suggestion of having just the exact same waveform from two different groups. Go through your entire process with the same waveform from two different groups. And it's a dumb error bar, but just say, well, this is the difference for these two groups. And so I'm not certain about my results up to this, at least this level, right? And this is sort of always the problem that, we always want to have just a single number that we can call our error criterion. Just get it under that and you're done. But it's not as simple as that. And so, I think we have to stop wanting to make it simple and face the complicated reality that, error budgets are difficult. And so we do need more exact, or more precise definitions of what we want for the error before we can say, okay, we've achieved it. Okay, we need to do this to get better or whatever. So, there are different objectives here. And so different catalogs might be better for different objectives. So, that's a reality that I think we need to face going forward. So, thank you.
Let me say something just very fast here. Sorry, Mike, but there is this point concerning the extrapolation. Exactly. We always use n equal 3. And so the model is calibrated to n equal 3. But there are other situations where we could get a very good agreement with UB quantities, like the fluxes, where we use the n equal 4. So we extrapolate during the inspire. I mean, this is an error. This is, I think, a problem that, in fact, we don't even know what we are doing and how trustable is our model, because you see, our models are tuned to your n equal 3 extrapolated waveform. So there is certainly I mean, we cannot do what you are saying. So yeah, if you are interested in the ring down, if you are interested in the inspire, I mean, in some sense we do, because for the ring down we use n equal 2 things. But globally, we have a mixture of everything, and possibly having all CCE extrapolated waveform would solve the problem one day. So I think that this thing used to exist in the past, because in the past I had used the data from the Llama code that with the Cauchy characteristic extrapolation to Scrape Plus, and this was very helpful. This allowed us to check several quantities, and this seems to me that is a bit disappeared from the literature, or I mean, it's not that the waveforms are routinely CCE evolved, right? So there is no real effort on this anymore after that Christian has left the, or well, you know.
So if Leo was going to respond to that, go ahead, Leo. I don't know if you just done. Well, maybe I'll just say
that I was going to respond to that.
Okay. Yeah, we are actually moving towards the next iteration of our catalog will still be extrapolation based, but I think after that we will move towards CCE. But even with, so we do believe CCE is better than extrapolation for a lot of reasons. But even CCE, you know, they're world tube radii to worry about and that sort of thing. And then, as Leo mentioned, there are BMS issues, and you know, if you want to do well on BMS, maybe you need a smaller world tube radius and that sort of thing. So even CCE isn't a silver bullet. You know, I don't think we're going to find a silver bullet. So just keep trying to get better in lots of ways is the goal here.
So maybe I can show up just for completeness. No, indeed, because I know that those papers and what is going on. But for example, since we are doing this discussion, so but people that are using the Einstein toolkit, are they CCE extrapolate things or not? I mean, is there an effort on this? Because I remember that I mean, we used those data that were from the Llama code, so it's Cactus in 10 years ago, and the waveform were pretty good. We could check energy and angular momentum conservation. We could really understand many things, and maybe this is something that could be routinely implemented in the Einstein toolkit community. I don't know. I'm not following anymore, so I might be saying very stupid things. So, but just something that would be very useful, I think. I mean, while you move, because then there is the BMS thing, that this is another. That there are other subtleties there. But from our point of view, already having other Einstein toolkit waveform with CC extrapolation of that could be useful. Just wondering.
Zach, do you know if there's anyone in Einstein toolkit doing CCE?
Sorry, just had to unmute myself. Well, we have a lot of folks in the room. Anyone?
So
anyone know? Yeah, go
this
ahead.
is Maria Hamilton, Maria Barbic Hamilton. I'm one of the developers and maintainers of the CCE, and I can tell you that nobody had any interest in using it. I haven't heard anything except for some graduate student a few years ago from a South African university. So yeah, the main reason is, and the thing that we did with CCE is to make it post-processing, because groups said that that is better, but it seems that this is not something that they want anymore. CCE is not fully parallelized, so maybe that is a problem. Maybe post-processing is something that they don't want to do, is an extra step. So, you know, laziness runs supreme. So for now, I don't have anybody. And also Josef Zlokor is also one of the maintainers.
Yeah, well, let's get to Josef to answer that. I know, Alex, you've been waiting forever. But I want to say something to Alessandro's point, because I saw his face when Maria said no one was interested. This is exactly the type of thing that I think the community should come up with. If you, as an EOB developer, says what would be really helpful, ETK, is if you did CCE, then I think you're going to see a big push that people want to do it.
Yeah, because, for example, just to conclude this point, no, modelization of the ring down, which is the real delicate thing. okay, I can trust SXS, I cannot trust SXS, it depends. Anyway, SXS gives you something with all the problems related to the usual things that we know. But for example, cactus, or I mean, I call it cactus, but let's say just for historical reasons, but okay, we know. You could do shorter waveforms with very highly accurate ring down, then extrapolate all this to infinity. This could give us, I think, a very good description of the late orbits, merger and ring down, also in the presence of eccentricity, for example. And this could be helpful because at the moment we don't have a modelization. I mean, in our eccentric model, we are using modelization of the ring down that are tuned to the quasi-circular case. It's true that more or less the system circularizes or that we like this, but there are details, and probably the tools are there. It's and I think I mean 7-8 orbits or even less with a good merger and ring down, CC extrapolated and all that could be useful. I think maybe not super exciting, but useful.
All right, thank you. I think that's the point. I feel bad, Alex. Please jump in, and then we'll get Joseph to talk. What's up, Alex?
Yeah, sorry, thanks. It was also on the whole topic about CCE, and so for those who know me, you may know I'm working on the hyperboloidal approach, which basically aims to put Cauchy problem and CCE all together and just solve it all together. So reaching future null infinity. And every time I give a talk, I find it difficult to say, okay, estimate, because we say waveforms are going to be more accurate once we get it working, obviously. Because of being able to extract that future null infinity and not need to do like the infrastructure to take the Cauchy eta and evolve them up to future null infinity. But I find it really hard to find any data on that, like any studies on how better CCE performs rather than just extrapolating. Well, I know there's some things, but I find it hard. And also, once we get this to work, I would like to be able to compare to the other options and to see, okay, how are we doing compared to that? Which is,
so
I guess yeah.
We do have a comparison paper.
Okay.
It's I have to find it on the archive, and we do show two things. First, that CCE is comparable to the extrapolation. We did it with the RAT extrapolation, and second, that CCE is the way it is in the Einstein toolkit is 1.5 accurate, and that's. That's a little bit worse.
Sorry, what does 1.5 mean? 1.5.
The convergence rate.
Okay, I see. Thanks. Would you be able to link me to that paper?
Yeah, I'll put it in chat.
Thanks very much. So yeah, that's what I want to say. And also I wanted to express that I thought that almost all waveforms actually had the CCE performed upon them, and I didn't know that it was so common to just have them at a finite radius. So yeah,
they're all extrapolated to infinity, but it's extrapolation, not CC.
Yeah, exactly. Okay, yeah, just for the future, because I think it's going to take a while until we get this working. Starting to see the light, but it will take a while. But I would really like to be able to start making some comparisons at some point. So I think it's something we also have to think about. Thanks.
Thanks, Alex. Good point. Joseph?
Yeah, I think most of what I want to say has already been said, but there is CC within the Einstein toolkit, but it needs a lot of improvements. But most of it, with the open source Spectre or CCE code, I think most of what's just needed is essentially being able to save the Einstein toolkit data within that format, which is not a particularly onerous task. So I would anticipate CCE being used more often in the toolkit now. I'm working with a student on CCE, so there's still some interest even within the Einstein toolkit community on that.
That's good to know. And the CCE code is spectrally convergent, is what Leo is telling us from his side. Thank you. All right, we have 16 minutes left. Mark, you had your hand up for a second, I thought, and I thought Deborah did too. Oh, and Adita, didn't you? Do you guys still want to talk, or did your points already get made?
Yeah, I mean, I basically put my point in the chat about basically about CCE and Leo mentioned that the Spectra CCE code can be used for post-processing any waveform, not just spec waveforms, and it's spectrally convergent, very fast. And also the thing that I wanted to point out in reply to Alex is that a graduate student at Caltech, Keith Mittman, has been working a lot with gravitational wave memory and has found, among other things, that extrapolated waveforms generally do not reproduce the memory, but CCE waveforms do. So in the future, if we care about memory, which we will once we have access to low frequency measurements like with LISA, we're going to really need CCE.
Thank you. I think that's where you're going to start seeing this swing that everyone's going to be interested. I mean, the truth was that LIGO Virgo wasn't good. This current generation, it wasn't an important question. That doesn't mean we abandon it forever. So it's good to mark these things down. Sorry, I'm trying to keep up with the chat and putting all this in the Google Doc. Did anyone else not get a chance to talk that wanted to?
I had my hand up earlier, but it was just a pretty significant shift from the conversation that was on hand because we started talking about the CCE stuff. And so I just put it down because it wasn't relevant at the time. But if we're ready to move on to a slightly different topic. So I just wanted, it was something that Deirdre already touched on, but it was in terms of just something that we need to think about. We talk a lot about, the accuracy and the things that are making our codes, less accurate, which places of error we need to address. But what comes down to it, and someone, I'm sorry, I don't remember who was saying it, was saying that we all wish that there was just one clear number that you have to keep for your error budget that you have to stay within, and it's never that simple. And yeah, that's the problem, is that we don't have, there are a lot of measures of what accuracy needs there are, but none of them, nothing one simple thing. So where I'm going with this is that we kind of need to understand that and understand what error bars we need to remain within. And if models need to remain within that error bars, and then they're training on our NR waveforms, what additional, then we have even stricter limits on the NR waveforms. And so this is something that my initial slide touched on, where I said that we need to think about the error requirements for detection, for parameter estimation, and for contamination issues, because all three of these will likely be different bars, and each of these will probably have many bars within them, boundaries. And so I guess I just wanted to make sure that this topic gets thought about, which is that we need to work together with the detector groups themselves, and for things like understanding parameter estimation needs, we need to be in communication with the astrophysics groups and think about what are the actual science goals, the stretch science goals, and how that's going to translate into error requirements. So we are, with most of us being numerical relativists, we're thinking of it at the base level, but we also need to kind of work from the top down of figuring out what those needs are going to be. And I think Deirdre also mentioned like working with the LISA data challenges to get an idea for how that's going to come into play. So I just kind of wanted to make sure that that topic gets thought about as well.
Go ahead, Jeffrey. Do you want to go ahead?
So I'm not a specialist. I'm in Aspen with a workshop, the Cosmic Explorer. And yesterday we had a work group that was talking exactly this thing. So compact objects, what are the science goals and things like that. So the first and most important one is astrophysical population. If gravitational waves can shed a light on this. What are the possibility that the gravitational waves will improve the astrophysics code that model those astrophysics populations? How the outliers that are going to be detected and are still detected, how those exceptional events fit in the astrophysical population. How do we understand the evolution, especially towards high Z? There is a lot of comment on energetics, EM energetics, and the fact that all the numerical results are useless in this point of view. So that was a very harsh observation. How black holes get their spins, how we can, yeah, I'll stop here.
I thought I heard someone speak. If not, Jeffrey, please. Maybe he didn't have anything to say, or he can't hear. I don't know.
I had two quick things I wanted to say. First, this discussion at Aspen sounded really interesting, and if there's any record that's on the web that you could point us to put in that Google Doc, that'd be great. I don't know if there is, sometimes there isn't. The point I wanted to come back to, I'm not sure this is the right forum to solve it, but I think it's the right forum to raise the question again, which is when we were talking about our audience earlier, like who is our audience? Another question related to that is how are we going to organize the work? So it sounded like, maybe I misread this, that maybe we're not so leaning toward working within individual experiment consortiums, like right? But then what is the right way to organize and coordinate? It's not a science question, but it's the management or people question. Do we want to have our own, like, is the numerical relativity community, like what entity is going to make sure that this gets done, or how are we going to make sure we work together? A separate consortium of numerical relativists, or a federation of numerical relativity collaborations working within the observatory consortiums, or just doing something much more freeform where different groups do what they want to do, and then it all comes out in the wash.
If we can have badges or buttons, I'm in. No, I'm kidding. And how does it get funded? Right. So I think that's always been a hiccup for us, and I know we're working on it, but we've tried this in the past. I think we could try it based on writing another paper on comparison. I mean, SXX is a huge collaboration. Einstein Toolkit is a collaborate. We don't really collaborate. I mean, we collaborate on that code, but there's not a lot of co-paper writing between everybody. There isn't a lot of, I see SXX is tighter than ETK. I would be willing to work with a larger group and attempt to do some of these things, however people want to. Do they want to apply for money? Do they want to just try to do it ourselves with all of our individual grants, just like the LIGO scientific collaboration is? You know, you don't actually get funding because you're in LSE, you get your own funding. Maybe we work with Pedro and other people and say, hey, how do we help this group, you know, stand on its own? I'm up for whatever. Anyone else want to comment on that? I don't know if Alessandra wants to comment on that or something else. I think it's a good point, Jeffrey, though. Alessandra, do you have a point to make? Sorry.
Yeah, very brief on what you said. Just that I think we need to understand, or you need to understand, to get all together, what are the scientific questions we really want to answer. Because it's not just a matter of comparing waveforms in the usual way or in the old way, but doing things in a different way. And there are things that some code can do and things that other codes cannot do. So I don't want to speak more about this here, but we need to think about what do we want to understand new from the
You don't
code.
want to do a combo, yeah, like it's nice when everyone's involved, but I agree, some questions are better answered by different things, so it can't be to restrict ourselves to those
Exactly.
things.
So because
Everyone can.
we cannot compare 20 orbits from one code to the other, there will be errors. Maybe things can be done, but thinking in a different way and making a different use of the current tools. I mean, something that I've been suggesting for years, but is really to compare for just to give you an idea, and then I stop. You have a very long way from SXS, can be very long, and then you could, for example, compare this with the chunk of waveforms from the Einstein toolkit, just short in spiral, some pieces where you put the maximum resolution that you can when the two objects are large, and so I think you can check. You could check several things. It's not just that the merge running down is okay, but that the in spiral are consistent, because the long in spiral of the SXS has not been checked by anything else.
5 minutes.
Thank you. Weird voice.
Oh.
Vaishak, do you have something you want to add?
Yes, hi, I'm Vaishak and I'm a senior PhD student at IUCAA, Pune. I primarily study the physics of dynamical horizons of black holes using the Einstein toolkit, and I just wanted to add a comment and also ask a question simultaneously. So I have been trying to develop or implement a code which does center of mass corrections, extrapolation, etc., using the Einstein toolkit waveforms. We have run 10 simulations of non-spinning black holes from mass ratios ranging from 0.1 to 1, a small set. And what I found was that, as was already raised before, the post-merger waveform becomes noisy when we use the extrapolation procedure involving a fit to polynomials. There are also perturbative methods, and I found that in the post-merger phase, they seem to be better. I just wanted to know what others' thoughts were on this. That's one part. And second part, I have also attempted to compare in a very crude way the waveforms from SXS, Spectre, Einstein toolkit, and RIT. Einstein toolkit meaning the waveforms from our simulations. And at a low resolution, which is the one available on Einstein toolkit gallery page, I found a disagreement of about 0.5 to 1% between the two waveforms. Thank you.
There's a lot of nuances in what people, and a lot of people use different things than what's in the public Einstein toolkit, even the people who are using an Einstein toolkit. So that's also a complicated situation. All right. It sounds like there's a lot of people doing different comparisons that it might be good for them to talk to each other. So I think this idea of moving a conversation to a dedicated Slack channel would be good, because there's these, it seems like we just don't all have a good sense of everything that's happening out there. So Leo sent the link. No one here is one of the facilitators for that in our community call, though. Leo, are you part of that? Someone, is it okay that we use it? I don't want to hijack.
Yes, I think it's totally fine.
Okay.
But I mean, but also we can make a new channel.
We
within
should
that
make a new
Slack
channel. I agree with that.
workspace,
Yeah, I'm
as
happy to
Deborah
make
suggested.
I'm happy
Deborah, you
to
wanna-
make that channel and add people. Any suggestions of names for the channel? Waveform requirements or something? Or I don't know how to broadly capture this topic.
2 minutes.
That sounds like a good name to me.
Okay, I'll go with that then.
Next gen waveforms is Jeffrey's suggestion if you're looking at the chat.
that one's pretty
That's
good, too.
because I keep saying 3G and Lisa, next gen is better, because then it's like that postmodern. Oh God, we can get really crazy. All right, we have 2 minutes. And I love this timing thing. It's like super serious. I keep seeing it count down, and somehow that means we have to be on time. Anyone want to say anything in closing? I feel like we have I agree with people saying, we got to pay attention to the detectors, we have to pay attention to the science mission. I think in the past for Ninja and NRAR, we all wanted to have a low bar so that we could have as much buy-in from NR as possible. I think if we try to work in a community, there's enough questions here that are open that we don't all have to work together. I think it's just that we have to somehow be able to send the same message as we go, like to all agree that, yes, we have said that, these waveforms are the best at this, or we have compared something here and we have a sense of what's important. So maybe we just need to be doing that instead of lowering the bar so down that everybody can have something to say. But anyone want to say anything before we end this? It's funny how intimidating that countdown is. I need the music from Jeopardy, Zach. Why don't you close this out, Zach? You're there in the
30
room.
seconds.
Absolutely. Yeah, so I'd like to thank everyone for participating in this very important discussion. I think it's certainly not the beginning of the end, but maybe the end of the beginning of this this discussion. We have a lot more, in other words, to talk about. And as has been indicated, we should be moving over to the Slack channel. I know there's also going to be a discussion at ICERM regarding this important topic. It may be restrained to only those who attend that in person. I'd encourage the organizers, if they could, to open up at least that discussion, like we've opened up our workshop here to the general community to participate. At the very least, I think we should continue to, as I said before, continue to chat over Slack, the appropriate GR community Slack channel. And I'll go ahead and leave this Zoom session open just for a few more minutes, just to make sure we get all the chats pasted into the shared Google Doc that Deirdre has so kindly created.
Except for the names. I didn't quite get the next gen versus postmodern, but I don't know if that's important. It's in there.
Cool.
I went
So
with
again,
next gen waveforms.
Thanks.
thank you, Deborah. All right, cool. Well, that's all we have. Thanks again for your participation, and let's continue this important conversation. Thanks.